in the last module, we had been looking at distance measures. Now, as we had seen, distance measures primarily depend on the type of variable that we are looking at. In the last module again, we discussed primarily the distances which are concerned with numerical variables. As opposed to what we will be doing today, we will be looking at distances which are for variables which are categorical by nature. Now, in numerical cases, it's easy to calculate distances because we have numerical values and we can look at the differences between these numerical values to measure a distance. For instance, if you look at the city block or the Euclidean distance, we take the difference between each element in the vector and either take the absolute value of them or the square of these values. However, this is not possible when we are looking at categorical variables because we don't have a numeric value in this case and we just have the frequency in each of these categories. So let us look at the categorical variables and the distance measures defined on them. Let us look at distances for categorical data. For categorical variables, it is easier to define similarity rather than dissimilarity. What is meant by similarity is whether the two individuals are of the same type with relation to a particular category. Now, usually similarity measures has almost similar properties as dissimilarity measures. So, this needs to satisfy the condition that CRS should be between 0 and 1. Also, CRR, that is the similarity between an individual and his own self, should be equal to 1. Thirdly, CRS can only be equal to 1 if R is equal to S. That is, between two individuals, CRS should not be equal to 1. And finally, CRS is equal to CSR. That is, the similarity between two individuals R and S is the same as the similarity measure for S and R. Going back to dissimilarity from similarity, we generally take the difference from unity. That is, DRS is usually taken to be 1 minus CRS. Let's start with the binary variables first. That is, we have two categories and we assume that all the m variables in the vector are of the binary type. Let's take m equal to 5. So, let's see what type of variables we can have here. Maybe the first variable is x1, which is male or female. Then we can have a second variable, which is whether the individual is young or old. In this case, of course, we are not looking at the exact age. Exact age would be continuous. We are just categorizing age as young and old. The third variable is tall or short. Greater than 170 centimeters means tall. Less than equal to 170 centimeters means short. X4, it can be light or heavy in weight. So, less than 60 kgs, the person is light. More than 60 kgs, he is heavy. And X5 is, suppose we want to see whether they wear glasses or they do not wear glasses. Now, the fifth variable in this case is slightly different from the first four. Because binary variables, we generally can categorize into two types. The first of this type is the present or absent type of variable. You look at the fifth variable here, wears glasses or not. So, some persons have glasses, that is, glasses are present in this case, and for some persons they don't wear glasses, so glasses are absent in this case. So, we can have a present or absent type of variable. as opposed to what is referred to as success or failure type of variable. Of course, success doesn't mean that not exactly in the English term, so we just call one of the variables, one of the categories as success and the other category as failure. So young may be success, old may be failure, or vice versa. Similarly, male and female, we can categorize them as 1 or 0. So in this case, of course, it's not like presence or absence. It's more of one of this characteristic or the other of the characteristic. Now, whenever we have this binary type of variables, the first thing that we always do is to draw what is referred to as a contingency table. So we form a table of the form, we have individual R in one side and individual S on the other side, and we have these two categories 1 and 0 on one side and 1 and 0 on the other side. So if we are looking at 1 1, this 1 1 cell corresponds with individual R having characteristic 1, individual S having characteristic 1, and suppose of the M characteristics there are A such characteristics in which both R and S have 1. Again, among the M characteristics, R has 1 and S has 0 in B of such characteristics. R has 0 and S has 1 in C of these characteristics, where both R and S have 0 have D such variables. So the sum of all this A plus B plus C plus D should come out to be M, and we also have what is referred to as the marginal totals. So how many individuals, how many characteristics equal to 1 does R have? It is A plus B, and R has 0 type of characteristics for C plus D of the variables. Similarly, for AS, we have characteristic 1 in A plus C of the cases and characteristic 0 in B plus D cases. Now, given this table, it's obvious that A and B matches for A if we have 1 1 or 0 0. It's a wrong match if it's 1 0 or 0 1. So primarily the measures are based on this sort of matching. Now again, there are three types of measures that we can look at. The first of these are the Jacob's coefficient is given by CRS is equal to A by A plus B plus C. Note that D is left out. I'll come back to this later on. Another measure is the Jankowski's coefficients. In this case, CRS is given by twice A plus B plus C. And finally, a third type of measure which is slightly different from the previous two is the matching proportion. In this case, CRS is equal to A plus D by M. Now, if you look at this three measures, the first of these two measures are usually used when the variables are of the presence or absence type, whereas the matching proportion is used when we have variables of the success failure type. If you go back to the previous table, you will see that D actually corresponds to the absence of the characteristic in R and the absence of the characteristic in S as well. So when we look at Jacob's coefficient, we exclude D because it's not present. So the measure actually is A. A means that both the individuals have this characteristic divided by A, which is again the same thing, plus B, which means that R has the characteristic but not S, plus C, which means that R does not have the characteristic but S has. So at least one of the two has the characteristic. So neither has the characteristic has been left out in this case. Similarly, for the next coefficient as well. Of course, in this case, we just take twice of A, but otherwise the measure is similar. Whereas in matching proportion, we are looking at A plus T. That is, either both the individuals have the characteristic present or both the individuals do not have the characteristic, divided by the total number of variables in this case. Let's look at an example. The first example, suppose we have m equal to 30. So it's a 30-dimensional vector. There are 30 characteristics which we are looking at. And the table looks something like this. So it's a present absent type of table, and there are 12 characteristics which is present in both R and S. There are 5 characteristics which is present for R but not for S, 7 which is present for S but not for R, and 6 which is absent in both R and S. So again we can calculate the marginals. So there are 17 characteristics which are present for R and 13 which are not present for R. Similarly, there are 19 characteristics which are present for S, but there are 11 which are absent for S, and there are 30 such characteristics. So in this case, of course, as we just discussed, we will be using either the Jacquard's coefficient, which comes out to be 12, because A is equal to 12, and A plus B plus C is 12 plus 5 plus 7, which comes out to be 24. So the value comes out to be 0.5. And similarly, we can have the Zenkowski's coefficient, which comes out to be 0.67. So we can say that the two individuals R and S are moderately related to each other. Let's look at another example. In this case, we take again m equal to 30. We have the same table here, but instead of presence or absent, we are looking at variables which are of the success failure type. Again, the same sort of table, but in this case, you see the interpretation is slightly different. So in 12 of the cases, both R and S have a success. In 5 of the cases, R has a success but S has a failure. In 7 of the cases, S has a success but R has a failure, and in 6 of the cases, R and S both have failures. So in this case, you can see that R and S matches in two cells. One is both have a success and the other is both have a failure. So in this case, instead of the previous two measures, we look at the matching proportion measure, which gives us A plus T, which is numerator 18, and this is divided by the total number of characteristics, which is 30, and this gives us 0.6, which means again they are moderately closely similar. Next, we go on to the multi-category variables. Now for multi-category variables, there is very little that we can do. In this case, we have variables like color. Color can be of different types. It's not two categories. It's not only red and blue or red and not red. It's red, blue, green, yellow. You can add on as many as you feel like here. It can be regions like north, south, east, west, maybe central, northeast, etc. It can be education, undergraduate, graduate, postgraduates, maybe school level, etc. And now in this case, if we look at two individuals, we can only think of matches. That is, whether these two individuals are exactly match in the sense that they belong to the same category or they do not belong to the same category. If you are looking at, for instance, region, whether a person comes from the north, another person can come from the north or may not come from the north. So if he comes from the north, the second person, then he matches with the first person, otherwise he does not match. So suppose R and S have k matches among the m variables we are looking at. Then a very simple measure of similarity would be k by m. This is the only possible measure that we generally think of in terms of multi-category variables. However, the problem is, given m characteristics, very often what happens is that some of these characteristics are continuous by nature, some of the characteristics are binary by nature, and some of the characteristics are multi-category. So what we need to do is, we need to find a way of combining all these sort of distance measures into a single omnibus measure. This is given by what is referred to as Gauss composite measure. Now, the Gauss composite measure assumes that out of the m variables, suppose m1 of them are continuous, m2 of the variables are binary, and we are assuming that it's presence or absence type of variables. M3 of the variables are multi-category. Of course, m1 plus m2 plus m3 should sum up to m. So, m1 of the total number of variables is continuous. We have m2 binary and m3 multi-category variables. And then the Gauss composite measure is given by this formula here. Now, this looks a little difficult to comprehend at a first glance, but let's have a look at this. If you look at the numerator, the first part of the numerator, which is summation j equal to 1 to m, 1 minus xrj minus xsj divided absolute value of that divided by rj. Now remember, xrj minus xsj modulus by rj is a continuous distance measure that we have already looked into. So we take, this was a distance measure which was for dissimilar variables, dissimilar measure. So we take 1 minus of that to get a similarity measure. And this we sum over all the variables which are continuous by nature, that is m1. And correspondingly we have a m1 in the denominator. Then the second term in the numerator is a. And again you have a second term in the denominator which is m2 minus d. Mind you, m2 minus d is actually, from the binary table, it's a plus b plus c. So it's a similar type of measure. So it's sort of a by a plus b plus c, now integrated with the m1 measures as for the continuous variables as well. Okay. And finally we have k, which are the number of similarities in the multi-category variables, and for this we take also have a component in the denominator which is m3. So it's k by m3, which was a multi-category measure, and that has been integrated into this formula to give us a omnibus measure. Today we have discussed measures for distances for primarily categorical variables. We started with the binary variables and we looked at what is referred to as a 2 by 2 contingency table and tried to define distance based on this. Later we shifted to the multi-category variables and found out how we can define distances again for this type of variables. However, in most problems, as we saw finally, there would be vectors consisting of all types of variables. Some of them would be continuous, some of them would be binary, and some of them would be multi-category. We have also seen how to get an omnibus measure for this type of vectors.